Today, we have Eghbal Rahimikia and Ser-Huang Poon from the University of Manchester, and they'll be talking about machine learning for realized volatility forecasting. I kindly ask them to say a couple of words where they work, what they do, and proceed with their presentation. Thank you very much and enjoy.
Yep. Hi, my presentation is about machine learning for realized volatility forecasting, and this is a joint project between me and Ser-Huang Poon at University of Manchester. First, I focus on introduction, some basic concepts about realized volatility forecasting, the model we are using. After that, we have data pre-processing, and later we are going to focus on forecasting instruction variables, and finally I focus on machine learning models and the conclusions. As a simple description of volatility, volatility is a measure for risk, and there are different types of volatility now. The latest one is realized volatility, and the realized volatility is coming from high frequency data. Research in finance shows that this kind of volatility has lower measurement error and noise, and the calculation is quite simple. There is a sampling frequency like every 5 minutes, and for every 5 minutes in high frequency data, we calculate the return, and using this formula, we can calculate the realized volatility. And this is a measure, as I told you, a risk in the market during that day, or when it's high, it means that the market is volatile, the fluctuations are quite high, and when it's lower, it means that the fluctuations are lower. So the definition is quite simple, and research shows that forecasting this type of thing, this volatility, is easier than forecasting return because it has more predictable behavior compared to return. When we check the research from 10 or 50 years ago, we have different types of models. We call them R family of models. These models are quite simple for realized volatility, and research shows that they work well, even if they are simple and even they are not using many variables, but the forecasting power, the forecasting performance is quite good. The base model is HAR model, or heterogeneous autoregressive model, and it's just considering past day or previous day realized volatility, the average of last week and the average of last month as input variables, and the output variable in this simple regression, OLS regression, is the volatility of next day. After Corsi introduced this model at 2009, different researchers propose different models here, like HAR-J by adding a jump component to the HAR model, or C-HAR or S-HAR, and latestly, the Boleslev proposed ARQ or HAR-Q models by adding more new variables. All these variables are coming from high frequency data. So this is still variables extracted from that kind of information, the time series of high frequency data. The main common feature among these models, as I told you, they are using the information from high frequency data like job component, BPV, positive and negative RV and RQ, and by adding these new variables, they show that the performance is higher compared to the previous proposed model. And also, these models are just using a simple OLS model for estimation. So it's not a complicated like machine learning models. Our previous research, you have access to this paper now. This paper showed that when we extract variables from big data environments, such as the extracted variables from limit order book data, which is a rich market information or data set, and also the variables extracted from news, because we know that the main point behind volatility is news. That's the news causing the volatility in the market. And the variables extracted from Dow Jones corporate news can help improve realized volatility forecasting. And in this paper, we added the variables extracted from these two kinds of big data environment to this simple model. So we are not using a complicated model here because of interpretation. We wanted to understand what's happening in the model, what is the relationship or interaction between a variable extracted from limit order book data and the next day volatility. But there are some questions here. The first question is that all these linear models, the simple models, sufficient for all the forecasting? Maybe we have non-linear relationship between these variables and our output. And also, because this is just a simple model, linear model, we can add many variables, like 400 variables at the same time. We have some technical or some theoretical issues in OLS, a model with 600 or 700 variables at the same time. But in machine learning, at the same time, we can handle this high dimensionality and at the same time, the non-linearity between these variables. So now from this paper, we are moving to a more complicated structure for realized volatility forecasting. And this is the data pre-processing steps. For both data sets, we applied many cleaning steps for cleaning the lobster data set, which is the main source for limit order book data, and Dow Jones Newswire, which is main source for news data. And we know that news data is ultra high dimensional data, and for this research, for this specific research, we use Langman dictionary for converting this news to sentiment, and after that we use these sentiments for our neural network. And for lobster dataset, at the same time we use crisp dataset in one step, and at the same time we have combined these features or these datasets and extracting different features and extract the daily data, because the main focus of this research is forecasting volatility in daily steps. We have some definitions here from lobster big data sets, and we applied many cleaning steps here. You can have you have access to the paper of this research later in this month, so you can read these steps. It's a bit complicated to talk about that, all these steps here, but this is just for cleaning the lobster data set, because usually lobster data set is sometimes, because it's generated by computers, sometimes we have some weird problems here, or some data are inconsistent with other features. So we need some steps for cleaning these data sets. And as I told you, we use crisp data set for removing the effect of stock splits, stock dividends, spin-offs, and other things. And the Dow Jones Newswires is a rich data news or textual data source for financial news, and the other type of news like political or weather, everything. But the main point is that this news is the news Bloomberg or other services are showing the traders in real time. So it's so important for the market to understand and for academia to understand the behavior behind this model. We have different tags in this data set to understand this news is related to our ticker or a stock or not. In this research, we are focusing on about. This is one provided feature from Dow Jones data set. It means that this news is about a company, but it's not considered particularly significant. The reason behind that is significant is so much better because that news is totally related to that company, but we don't have access to significant, I think, before 2014 or 15, because Dow Jones moved from an old structure tagging to the new one. So we are using about because of our time span is longer we are analyzing here. As I told you, we are using Langman and McDonald dictionary. And we are extracting different, this is the latest dictionary, the latest version of this dictionary. We have access to 2018, and we can convert or translate every news based on dictionary to different sentiments, from negative, positive, uncertainty, and many things, modal and ambiguous. And we have this weighting scheme here for normalizing, or like, because sometimes we have some words, we have more repetitions of those words in our data set, and for other words we have less repetition. So we should have this weighting scheme, and this is the proposed weighting scheme from McDonald and Longman. And forecasting structure, as I told you, is dative forecasting. Our time span is from 2007 and 2016. We are focusing on rolling window forecasting. Our out-of-sample data contains 300 days. For estimation sample size, the time span I told you, we are using near 2046 days. Our sampling frequency for calculating realized volatility is 5 minutes. We are focusing on 23 stocks or TK from NASDAQ market, and these tickers are chosen based on they have highest liquidity and at the same time the availability of data we have. Also, we are following our paper, Rahimikia and Poon, and because this paper showed that sometimes it's usually for realized volatility, it's better for reporting the results. It's better to discriminate between normal days and jumps, because usually this is one of the main features of volatility. We have many days with low volatility, and at the same time we have few days with high volatility, and this is the distribution. The distribution is totally different with other variables in finance. And also, as the next step, we are using the reality check of White with 999 new sampling at average block length of 5 for comparing every proposed model with all our family of models together. So if we have something like 100 based on reality check, it means that for 100 of our cases, it means that for all 23 stocks, our model is working better or has better performance compared to all other proposed models or our family models from AR, CR, RJ, all of them. So it's beating all of them. And for the loss functions, at the same time for proposing the models and for the general model and also for the robustness checks, we are using mean square error and Q-log, because patents showed that these are the main two loss function for ranking, the best loss function for ranking the realized volatility forecasting models properly. So again, you can refer to the our paper later and the patent paper to understand the details about these loss functions. For machine learning models, we are focusing on different group of variables. The first group of variable is here, our family of variables. So these are the variables extracted from those simple models. So they put all of them together, and we have one group of variables here. Number of variables, we have 5 variables here. For order book and message file variables, we are focusing on these variables extracted from this paper. Here we have totally 134 variables, as I told you, because now we are moving to machine learning. We can use more variables, high dimensional variables, for training our models. And for the third group, we are using the variables extracted from news data. So we have 9 variables, different sentiments in the news here. This is the descriptive statistics, or this is the cleaning statistics of our realized volatility. As I told you, we are applying different steps for cleaning our realized volatility data set because of those problems in the data set we may have. So we can see we are nearly cleaning 45 or 50% of our high frequency data in our data set. So now our data is clean and ready to use. These are the descriptive statistics for every symbol or every ticker we are using for realized volatility forecasting. This is the structure of our model. We are just focusing on long short-term memory. The main reason is that we can use more complicated models for designing this model. Like, you know, there are different models. We can add different things to this model, different layers of long short-term memory, the other layers we can use this model. But if we move to that step, the interpretation, the understanding of this model is going to be more complicated. And also it takes more time for training. Just think about that. I think for this research, we train more than 600 or 1,000 models, and it takes so much time because of the data set we are using, for the high number of variables we are using to train these models. And as you know, we talk about that. We are training the model every day, and after that, use this model for forecasting the next day. And this is happening because this is rolling window. For a simple linear regression, it's quite easy. But when we move to machine learning, so time consuming. That's why we train all these models on servers. It's not possible to train, you know, these models on a personal computer. So we have long short-term memory. We are considering 21 lakhs here because it's consistent with the amount of information we are using for our family of models. So they are using maximum 1 mount as the input variable there. Here we are using the same thing. This is the general model we are proposing. Later in robustness checks, we are restricting these models, or we are modifying these models to understand the behavior of realized volatility based on machine learning models, because, you know, machine learning, or especially here neural networks, are quite flexible. And so sometimes someone can criticize that. So you are just considering different units. Like in this research, we're considering, if you check this one, we are considering just 5, 10, 15, 20, and 25 units. And someone may tell us, okay, so if you use different number of epochs, because here you are just focusing on 50 epochs, if you change this one, maybe your model may work better. So for the robustness checks, we are considering all these different definitions, different properties of the models. At the same time, someone may criticize us here. You are using more information here compared to our family models. There are just 3 simple, for our family models, we are just consider 3 or 4 simple variables. But here you are inserting so many variables at the same time. So definitely this model is going to win or beat those models. But again, that's why in robustness checks, we are trying to make this model simpler, like just using realized volatility, just one variable for forecasting realized volatility. And we can see, I'm not presenting those robustness checks here because the majority of our paper focuses on those robustness checks. And I think this is the main point behind the machine learning. We should change this model, make it more comparable with those simple models in finance, which researchers show that it works fine. Because now we are using servers, it takes more time. So someone may tell us, what is the benefit of this model? So that's why we are considering different variations of this model. But this is just a simple structure, general structure we are using. You can see the properties now we are using for regularization, or the loss function we are using, and the other things. And we can see when we move from linear models, we have high number of parameters to tune, and also high number of variables we are considering for different units or different types of machine learning models we are training now. And this is totally normal because this is just a simple model and we are just optimizing, finding those coefficients in OLS. But here we have different base and weights and biases in neural network we need to train. So I don't want to focus the details. As I told you, you can refer to the paper, and it's a bit a bit long paper to read, but here I'm just focusing on some basic results we can present here in this short time. Here, the first part, this part is focusing on the machine learning model trained only based on the variables extracted from Haar family models. This one is adding news, those sentiments to those models as the input variable. This one is adding order book, that 130 something variables to the Haar family models variable, and this one containing all the variables we have. So all these models, group of models, the base variable set is Haar family models variables. Here we are adding news data, here we are adding order book variables, and here we are using all of them. This one is the results for jumps, the results for normal days, and this one is results for jumps. And here, based on our previous paper, we are just focusing on a simple method, interquantile range, for discriminating between normal days and jumps. And you can again refer to the paper for understanding more about this method. And those bars are reality check. As I told you, if it's something like 100%, it means that for 100% of our tickers, our 23 tickers we are analyzing, this model is beating all Haar family models. And at the same time, our previous research showed that C-Haar model is the model with the best performance among our Haar family models. And that's why we are comparing every model, every machine learning model with the C-Haar model. So these are the average. The red line is the average, and the blue line, I think the red line is average, and the blue line is the median. And also we have here, we have machine learning with 5 units, 10 units, 15, 20, and 25. As you can see, for all of the cases, machine learning for normal days is beating all those Haar family models. So the machine learning is winner for normal days. And for 100% here, if you see that these models, for 100% of stocks, it's winning compared to the Haar family models based on reality check, because it's near 100%. And if we just consider the improvement, the amount of improvement, we can see when we add limit order book data, it's lower. If it's negative, it means that the improvement is higher here, and we are reading the negative value from here. But when we move to jump, it's not working well. So those linear models are better for forecasting jumps. We can see when we increase number of neurons, number of units in our long short-term memory, we have improvement in the performance, but still it's not that much. And again, at the same time, when we can see, when we are increasing number of units here, we have improvement here for jumps, forecasting performance, but we have degradation in the forecasting performance of normal days. So there is a trade-off here. We can add more units for improving the forecasting performance of jumps, but at the same time, we are losing the performance for normal days. So this is one important finding, and this shows how important is the selection of those parameters in machine learning, and it's totally apparent here, transparent here, that is affecting our performance for normal days and jumps at the same time. These are the results for mean square error, and results for Q-like are similar, mostly similar. And the other way we can show our results based on our previous paper, because we are just focusing on average, it's not very transparent. We can have a radar chart like this one. We have different tickers here, and we can show the improvement based on mean square error and Q-log. I choose just one model here, the machine learning model, which using the news data and order book data with 10 units. So it means that we are just focusing on this model here. One of the best models here I choose for this step. And we can see that when we are inside of this bold circle, when the values are negative, it means that we have improvement. When we are outside, we have degradation in performance. As I showed you here, we are just focusing on comparing our model with just Ser-Huang model. But here, because I showed that Ser-Huang model in my previous paper is the best model among Haar family models. But here, I'm comparing it with other models too, so it's more transparent. You can see machine learning for mean square error is beating all those models, and at the same time for Q-like is happening too. All of them are inside of this circle, and it means we have improvement. So this is a better transparent. These values are not coming from a data set, the results. So sometimes it's just for 2 or 3 tickers, the model is winner, but for the other models, it's not the winner. And we can see this here transparent. But here, when we are comparing all these stickers and all these models at the same time, it's more transparent. So we can say definitely that for normal volatility days, machine learning is better. But when we move to jumps, it's not good. We can see that for most of the tickers, even considering different Haar family models outside of the circle, it means that it's not working very well. And even for some of the stocks like MU, this is one of the stocks we are considering, the degradation, the performance is quite high. And later in our paper, if you refer to that, we are talking about that why this is happening. Why for one stock, the degradation is quite high, near 500 points. And these are the things I will talk about, that the trade-off between loss function and everything. And just for one example, I'm just talking about that ticker with high degradation. If we come back to RV descriptive statistics, we can see that this MU, this specific ticker, is like outlier among all other tickers. It has different distribution of realized volatility. You can see the median is the highest one, the first quantile is the highest one, the max is the highest one, the minimum is highest one. So this is so we are investigating this abnormal, this outlier behavior, and we can see that this is the reason behind that, is that this behavior is totally different here, these statistics. And this is it's a nice representation of the models. We have different tickers here, and this is the true RV, true realized volatility, the real values. This is one of our models with 10 units, the other models with 25 units, and this is our simple Ser-Huang model. And we can see that Ser-Huang model is better. These dots, these points are our outliers, our jumps, based on our definition. We talked about that in our previous paper, interquantile range. And we can see that nearly all of these models, they are not able to detect those jumps. Ser-Huang is a bit better. You can see it's detecting some of these jumps here, but still it's not possible for these models to detect these jumps. Usually they are happening during the financial crisis, these values near 100 or something like that %. So all of these models are not good for detecting these jumps. And at least we know that machine learning models based on the presented results are at least better than for normal days. But if you want to use these models, these basic models for detecting those jumps, it's not. All of them are not good, but linear models are a bit better. So I just want to tell something here is that it doesn't mean that machine learning is not good for detecting jumps. This model, which using all data set together, normal days and jumps at the same time, is not good for this task, but it's good for detecting normal volatility days. So maybe we can later train a new machine learning model for just detecting these jumps. And maybe, I'm not focusing on that in this research, but maybe it works better. So we are not rejecting machine learning this model for detecting jumps. It means that maybe we need a new model for detecting jumps. Putting all data together is just good for improving the performance for normal days. And again, for proving that this is right, because mean square error and Q-like are not focusing on the direction of our forecasting performance. Here we are focusing on mean directional average, and we can see here, for most of the machine learning models, we have at least something like 8% improvement in mean directional average performance. Again, this is for normal days, near 100% based on reality check. And for the jumps, again, it's not very good. But we can see for normal days, it's brilliant. The model is so good for normal days. And I should tell you, if we check the statistics, 90% of our days are normal days, 90 to 95%, and just 5% of days are volatility jumps. So this model works significantly better for that 95% of days. But for that 5%, if our focus in industry or academia is detecting those jumps, it doesn't work well. But if our focus is those 95% of days, it works very good, as it can significantly, statistically significant, is working better than the other models. And also, we propose different models in our first paper, as I told you, just adding variables, simple variables extracted from limit order book data and news variables to those simple Haar family of models. In that paper, we showed that this is so good. When we add more information, we are improving the forecasting performance of normal days. And this is it's so interesting. When these are the models we propose in the first paper, and these are the models we are proposing here. And we can see when we move to machine learning, it's going down. We have a drop here. It means that we have a sudden improvement in forecasting performance of realized volatility for normal days. And again, the reality check is going up. So it means that machine learning can beat even our proposed models, those simple linear models in the first paper. But again, for the jumps, we have the same behavior. It's not good for jumps. If we want to focus on jumps, it's better to focus on our proposed in the same paper. Those models are working better for jumps, but machine learning is working better for normal days. Again, we have the same behavior for Q-like. And also for the last step, I'm not presenting these steps here, but as I told you, the main point behind machine learning in finance is robustness checks, because people can criticize us. You are just using one model with this kind of parameters. If you change it, maybe it's going to be different, the behavior and everything. And also you are using more information. So for robustness checks, if you refer to the paper later, we are using restricted information set. It means that except using 21 or as 1 month of variables or 1 week, we are restricting our machine learning variables to just using 5 days or one day, previous day as input data. Again, we are comparing these models with the Haar family of models with 21 lakhs or 21 days as input variables. And again, we show that machine learning is winner here. Again, for the next step, we are just using 21 day as historical realized volatility. So here, I'm not considering the news coming from order book data or news information coming from news data. I'm just considering realized volatility, the history of realized volatility for forecasting the next day volatility. And again, we can see this simple model. This is kind of simple model in machine learning because it's just using one variable, not a high dimensional environment of variables. And we can show that this simple model again can beat all those Haar family models. Here we are switching, because one flexibility behind machine learning is training function or loss function. We are switching from mean square to Q-like and compare the performance. Here, as I told you, we are just in the main model, we focus on just changing number of new units for the next robustness checks. We are changing number of epochs too. And we are comparing the models and at the same time moving to individual in the stock analysis, like those radar chart, and see the behavior, what's happening inside. And for all these models, we can see machine learning easily can beat all Haar family models and extended Haar family models. They propose extended Haar family models from our previous paper. But again, for the jumps, it's not very good. So for the more information about the details of this paper, we are going to publish this paper later this month or in the beginning of the next month. The title of this paper is Machine Learning for Realized Volatility Forecasting, and you're going to have access to this paper. And for now, you have access to the first paper if you are interested. Our first paper is available, but this paper is just focusing on the machine learning I'm presenting here. Thank you so much.
Well, thank you very much for your presentation. And now we will move to the discussion phase.